a long day today, the longest day of this workshop, and so we have in the morning 5 speakers and 6 speakers in the afternoon. So good luck. And so our first speaker is Michael Ghil, who will then chair the morning session, extreme events and coupled climate economics model. Please.
Well, as chairman, I consider that what I have to say is much more important than everybody else's. So Valerio is going to have to keep me from that conviction. Okay, good morning. Thank you very much for those of you who have actually woken up on this first British day. You know, weather has become suitably lousy, so there's nothing better to do than be here. Okay, so this has been very, very interesting so far, and thanks, I guess, it's like the Academy Awards. We have to thank the organizers, the Institute, Sir Michael Attia, PRS, founder of this institute, etc. So, having said all that, things have been sort of pretty mathematical most of the time so far. So I will try to instill a sense of reality. This is joint work with a fairly large number of people, and the different colors indicate collaborations to different aspects of the work, but I won't take any of the precious time. Okay, so I started at 05, remember, okay? Okay, okay, okay. So I'll skip the jokes about my 2 affiliations, and actually this is the logo of these are the 2 institutions, and this is the research group at UCLA. Yes, if any of this is of any interest to you, you'll find reprints and preprints and whatnot, mostly here, but also some complements over here. Okay, so what about the coupled? Well, some of the motivation has to do with the fact that the IPCC process, anybody here who doesn't know what the IPCC is? Good. They haven't contaminated the whole world yet. Okay. That's the Intergovernmental Panel on Climate Change. Okay? Pardon me? No, not gonna. Okay. So, which has just started unveiling its 5th assessment report this past late August and September, with the working group 1, which has to do with the physical science basis. These are the covers. Each one of these is a thick report like this from the last time, the AR4, you know, the assessment report number 4. So these are the covers, you know, physical science basis, impacts, adaptation and vulnerability, mitigation of climate change. And the reason there are 3 working groups is, well, first of all, because the people involved in this are more and more numerous, but then also because they don't speak the same language. And actually, I remember the first time when I was at so this is my little I&I anecdote, you know, following in the footsteps of Mark Pollicott. You know, the first time I was in Cambridge, at the I&I, not in Cambridge, was when it didn't have this beautiful building yet. It was in some other place that nobody seems to remember. I remember sitting in the library, the well-furnished library, you know, sort of club chairs and so on, and looking at the biography of Wittgenstein, who, of course, taught here. And, you know, it is Wittgenstein who attracted the attention of the officially thinking world to the importance of language in communicating between people who write what they think. So, you know, that's end of anecdote. It's hard to talk if you're a mathematician to anybody else, and if you're a physicist to a social scientist. Okay? No? You didn't notice that thing? No? It's hard because they think differently. So part of what we're interested in here is sort of overcoming this barrier, and we aren't done, but we're still thinking about it. And I won't have the time to talk about ethics and policy issues. That's actually the green corresponds to this collaborator who's now at TU Delft. Okay, so I will start with climate change and other natural hazards, of course global warming, but extreme events in the atmosphere, ocean, and solid earth. And then most importantly, or at least the most different from what other people have said so far, is these extreme events, which kind of economy do they impact? So much of the talk will be about this eventual dynamic coupling, but in particular, it will be about so-called endogenous business cycles, or EBCs or ENBCs, versus quote-unquote real business cycles. I'm going to tell you where the quotation marks for the real come from. And then one of the reasons of talking about it here is that there's a vulnerability paradox and a nonlinear or out of equilibrium fluctuation dissipation result, which is looming large in this business. And I will talk about data as well as models, and conclude with conclusions and some bibliography. Okay, so the little that I know about extreme events, I have learned it at great cost to the European community from a European project called Extreme Events, Causes and Consequences. And this is now some more specific motivation that launched us into this project. So this was already mentioned a number of times, but I'll have more to say about the rarity of extreme events, an obstacle as well as an incentive. Extreme events is a manifestation of complexity, so we sort of all agree that we're not talking about maxima and minima of smooth functions. We're talking about something that's truly extreme in some sense, and that is a manifestation of complexity, in other words, nonlinearity, interaction of various things, etc. And so it is actually becoming clearer and clearer, even in the IPCC process, that we are not that interested in global change, in global temperatures. We are very interested in global change, not very interested in global temperatures. Nobody lives at the global temperature, but what people do experience is, well, variability and extrema. So we're interested in statistical analysis and modeling, and there will be, again, a little bit of a question about deterministic versus stochastic. Well, there is, as computers become bigger and bigger, certain people become more and more ambitious about putting everything into them, what we call in the United States a kitchen sink. And so there are Earth system, there's not just climate modeling, but Earth system modeling, including vegetation and all sorts of other things. And beyond that, one would like to even go to coupling, say, socioeconomic with natural phenomena. One of the reasons for daring to confront all these challenges was because we have a new integrated modeling tool, Boolean delay equations, which I will just have a couple of slides on, simpler and more flexible than the more standard, flows. I mean, ODs, PDs, SDs, etc. And eventually one would like to predict. I mean, one of the many ways that one says that this species, which is invading more and more of the Earth, is different from the other species, is because it projects itself into the future. Okay, so there's even this website, which I think is still active, although the program has been over for a while. So here is a few fashionable extremes, extreme pizza, X. This is a rock group called the Extremes. This was a cover of Time magazine some time ago. Locked and Loaded, the secret world of extreme militias. You put black stuff on your face, and you get not only a Kalashnikov, but also a tank, or at least a rocket launcher, and you're an extreme militia. Okay, and then there was even a very beautiful exhibition at the Maison Européenne de la Photographie, a very good photography museum in Paris, called Autour de l'Extrême, around the extreme. and I won't show you some of the photographs that you could see there. Maybe you find them on the web. Okay, so a quick outline: what we started with, what we did, what we found out, and most importantly, what we'd really like to know and don't know yet. So who we were and what we started with. Okay, so these are, this is a contribution of Bruce Malamud from King's College. These are the flags of the 9 countries involved. It's not quite like the IPCC. I remember that when the AR4 was announced, you would go on the website of the IPCC in Geneva, and there was a light flashing, as if it were a Walmart sale. Said, 1,700 scientists, 500 pages, one report. Okay, so it's not quite like that, but it was for a very small price of 1.5 million. 17 partner institutions in 9 countries, tens of scientists and junior scientists, etc. So with all this effort, you're going to see that I didn't learn much. So don't worry. Okay. This is of substantial importance to real people who have real money, namely the reinsurers. Okay, so a reinsurance company is a company that insures the insurance companies. So it needs a lot of money. And so they are concerned about natural catastrophes. This is out of a report of one of these very large companies, Munich Re for reinsurance, Topics Geo 2003. So these vertical bars are each one for a year, and they're divided into colors. Red is earthquakes, volcanic eruptions, green windstorms, blue floods, and yellow others. There does seem to be an increasing trend. Okay, it is possible, one of the statements about global change, and this statement goes back to the 70s when the fear was actually of cooling, not of warming, that...
What is the vertical axis?
Pardon me?
What is the vertical axis?
The what?
Number of events, or is it the cost? Or?
Number. No, the cost is clearly going up because there's more and more stuff that is being insured. And this are just events, not, in developed countries, it costs money. In less developed countries, it costs lives. Okay, there's some of a dichotomy in that. So this is just number. Okay, so as I said, going back to the 70s, there was a feeling that as the mean moves, the variance also moves, and they're more extreme, etc. In this case, it is not clear whether it is simply better reported or whether there's a real increase in these events. There does seem to be an increasing trend. If you look just at the earthquakes and volcanic eruptions, they stay pretty constant. So maybe it is true that the warming does something. Okay. So key ideas: describe, understand, and predict extreme events. Combine expertise in complex systems with broad knowledge in the natural and social sciences. These were the main study areas: natural disasters of all these different kinds, socioeconomic crisis, and finally the one that I'll talk about most, interaction between economic and climatic changes. So I'll skip the rest of this slide in the interest of the following speakers. Okay, so this is what's called a frequency size distribution. There's been already talk about this and number. I mean, a lot of what I have to say has already been touched upon in the previous days, which were very full and interesting. So basically, on a log-log plot, this shows, the red dots are the actual numbers, and the blue line is a least square fit. U.S. wildfires, U.S. and Italian rockfalls. Why U.S. and Italian? Because there were 2 of those flags at the bottom of one of the slides. And there are many things which fall on such straight lines, and there's also a saying that there are 3 kinds of liars. There are occasional liars, systematic liars, and people who plot stuff on log-log plots. Because clearly this is a factor of 2 or 3 away from the straight line, Anyhow, Now, this is actually, oh, here the two colors correspond to Italy and the US. And so this is the sort of stuff that is referred to in practice when an engineer says that she, he, or it is planning a building for the 100-year windstorm or a bridge for the 50-year flood. You know, you go somewhere here, okay, and you find how many of these events have occurred over the past, and maybe you do a more sophisticated analysis of recurrence time, and then you decide, how much steel you have to put into it. But in some sense, we wanted to go beyond this, okay, beyond this form of probabilistic hazard forecasting. So how do you go beyond that? Well, one of the things that I will have to say is about two different ways of looking at time series. So I will illustrate this with the Nile River floods, which are the longest climatic, quote-unquote, instrumental time series. The instrument here is, and no associations, please, is a nilometer. This is a column. There were many of these in ancient Egypt. When I say here the longest continuous instrumental record, it's more or less continuous, and I'm just talking about 1,300 years. There were records in Pharaoh's times, but there were very big gaps, so we're not going to talk about that. So this is the instrument, and so you see when the flood reaches its highest level, this man climbs on the back of a woman, which is the way you did science at that time and still do to a certain extent today, and he hews into stone the level, which happens to be 17 cubits. Okay, and this was a big thing not just for Egypt, but also for the entire Mediterranean. So this is a mosaic from Galilee, okay, from roughly the 4th century AD. Now, clearly, this is related to Pharaoh's dream and Joseph's explanation thereof. You all remember, you've all had the Old Testament, right? So, there are 7 lean cows and 7 fat cows, and the lean cows eat the fat cows. And Pharaoh had this dream, and Joseph explained to him that this is 7 years of plenty and 7 years of droughts, and so this was the first forecast, climatic forecast documented, and the first adaptation and mitigation story, because clearly you were supposed to store during the years of plenty for the years of drought. So if with respect to time series analysis, I will just talk about effects of periodicity and of long-range dependence, or LRD. Okay, so here is one kind of analysis. So I call this, the rough versus the smooth part of a signal, and I will explain what I mean. So, you look at here at the periodogram of the time series of Nile River minima. So again, this is frequency versus spectrum, and well, you manage to draw one straight line, actually even 2 straight lines, which correspond to different models that have been used in looking at what I like to call the rough part of the record, the jumpy part, and which basically in the spectral domain corresponds to the continuous part of the spectrum. So here are two of these lines, fractionally different, Red model versus Hurst exponent. So Hurst was the guy who was really worried about these things and wrote a book about the Nile, and I don't know exactly who stuck his name onto this exponent, but in any case, Benoit Mandelbrot talked a lot about the Joseph effect and this sort of kind of analysis of long-range dependence. So this illustrates the rough part of the record and hence a smooth part of the spectrum. Mark Polycott photographed himself next to Paley's grave. I didn't know that Paley died of a skiing accident at a very early age. But Paley-Wiener theorems essentially talk about the connection between the smoothness of things on the one side and on the other of the Fourier transform. Now, number 2, okay, if you look at this with 2 methods of spectral analysis which people throw at time series when they are not long enough in order for Fourier transform or discrete Fourier transform to do the trick, because essentially in Fourier analysis, the height of the peak is, or the error bar on a peak is proportional to its height. So almost by definition, you don't get a lot of certainty out of that type of analysis. So these are two types of analysis that one does in order to compensate for these difficulties of shortness and noisiness of climatic records. So looking at high water level and low water level and doing these two kinds of analysis, you get a peak. So it was already well known that there is an El Nino Southern Oscillation or ENSO effect. You know, one of the sources of the Nile is a blue Nile that originates on the Ethiopian plateau, affected by easterly winds from the Indian Ocean, affected by the Southern Oscillation. And so there is a peak at around 2 to 3 years. And this is another one that we found here. Actually, that picture comes from the cover of the Geophysical Research Letters where this paper was published. And so we found another peak at roughly 6, 7 years. So maybe that has something to do with Pharaoh's dream, more than what Benoit Mandelbrot called the Joseph effect, because Joseph didn't talk about long-range dependence. He just talked about 7 years and 7 years. Okay, so this is one aspect. Oh, and I should mention that if you want to do this kind of analysis and you have not subtracted from your time series the trend and the periodic components, you are very apt to make big mistakes. So this is just a practical take-home advice. You know, if you like that kind of analysis, don't forget this one, take this out, you know. If not, the peaks are going to contaminate your analysis of the continuous background. Okay.
May I ask you a question?
Yes?
So if we want to know how Joseph was right to speak about the 7-year cycle,
Yes.
basically it's a question of order of magnitude of how high is this peaks.
Yes.
So can you answer this question?
Well, as I said, the trick in these things is that in different ways, the variance is not simply proportional to the height of the peak. So there are, you know, there is this toolkit that I didn't want to talk about here, in which we have these two methods, and the point of the toolkit is statistical significance tests. You know, because as Robert Votard, who was my co-author on the first papers of SSA, likes to put it, writing the code for SSA is 12 lines. The trick, you know, the devil is in the details. I mean, in statistical significance. So, you know, I have a little page that I'm willing to send to anybody that says, you know, 10 points that you need to worry about in when a peak is claimed. Okay, you start with a time series on one method. You play with the parameters, then you'll take another time series, you take another method, you know, and eventually you have to have a physical model. You know, real confidence is provided. No matter how good your statistical analysis is, when you really believe it is when you have some understanding of why the peak is there. And I can tell you that for the 7 to 8 year peak, I have at least a plausible explanation that we've worked on. Thanks very much, Freddie. Okay, so what we did, so this was part of what we did, what I just showed you, but this is just a review paper. So again, you know, there's a huge literature of extreme events, but you know, this is not such a terrible place to start, and there are actually people in this room who have been co-authors of this, I think, and Dmitry Kondrashov, whom you heard, and so on. And somebody, I think, comes from the institute in Göttingen, where Annette Wittner is. Okay, so, you know, it covers much of the material that I'm talking about and other things. So there were 120 papers in referee journals and all sorts of other stuff. Okay, what we found out, well, so again, we're sort of interested in prediction, okay, In forecasting algorithms, for might be just as well good for natural and social systems, can we beat stochastic-based approaches? And so basically, again, there are these two complementary approaches, one which deals with periodicity, the other one which deals, if you wish, with something called point processes that earthquakes and volcanic eruptions and maybe riots are. And so in order to go beyond probabilistic prediction, as I said, you really would like to have some physical or socioeconomic models. So here are some examples of such models. You know, here is a middle model for seismic events, the slider block model of Bob Burridge and Leon Nopov, which is sort of the solid Earth counterpart of the Lorentz model for atmosphere and oceans. And here are some cellular automata models of forest fires, or if you wish, lattice models. So green points are lattice points or boxes where the trees are healthy, and red is where they've burned. And, well, you know, people, I mean, physicists do like simple things that they feel they can say a lot more about than the people in the actual field. So there are, in the physical literature, papers that talk about forest fire models, which are essentially Ising models or something like that. And again, Bruce Malamud likes to say that the forest fire model is not a model of forest fires, because forest fires are much more complicated, you know, than this sort of stuff. So we also published a paper in the PNAS with a grad student from the École Normale, etc. So, you know, simple models, ordinary differential equations, cellular automata, and Boolean delay equations can help us understand and predict. So just a couple of slides on Boolean delay equations. Difficulty in formulating classical models, not so much because it's hard to formulate the models themselves, but because this type of models typically confronts you with a difficulty of inserting numerical values of parameters which come up. And very often it is very difficult to have the parameter values, while in these Boolean delay equations they are simpler and more flexible. There'll be the next transparency, the next slide, that I'll tell you exactly what they are. But basically, the only parameters are the delays in the actions between the various variables. So again, this is a fairly large number of people that helped me play with this. This is just a diagram that sort of shows you the place of PDEs in dynamical systems. So you have flows in which the state is continuous and the time is continuous, so vector fields, ODs, PD, etc. Maps in which the state is continuous but the time is discrete, so diffeomorphism, and actually ordinary difference and partial difference equations. Most people don't realize this, but you know, a numerical model on a computer is really this. It is not that. In particular, general circulation models. You know, whichever way you discretize, you cannot typically do things in continuous time. You can do it on analog computers, but very few people still use them. So it's very important that you can not only go from here to there by discretization, but under suitable mathematical circumstances also back up by a process called suspension. So, you know, it's in some sense easier to analyze these when they're simple enough, but you would like to be able to transpose the results to the things that you believe actually model the world. You know, where's a portrait of Newton? You know, I'm going to okay, do an obeisance to Newton, you know, who made us believe that these are the right things. So as I said, the automata in which both the space, variables are discrete and the time is discrete, you know, Turing machines, real computers, cellular automata. And then finally, there was sort of a missing corner in which the variables are discrete, but the time is continuous. And it turns out that these are quite interesting. One of the reasons that they're quite interesting is that, for instance, cellular automata, all sorts of things about universality of behavior have been claimed. Those are only true if the cellular automaton is infinite. Any finite cellular automaton can only have fixed points and periodic solutions, okay? Because for a fixed length of word, the word will repeat itself as you proceed in time. So, we actually use these Boolean delay equations on networks, and this is just a beautiful illustration of the different kinds of networks. You know that this is a very popular topic these days. Maybe Jürgen will tell us more about, Jürgen Kurtz will tell us more about that. But again, I don't have the time to go into the results because I really want to get to the part that I think is most interesting of the talk, for which I still have all of 5 or 10 minutes. So, received wisdom, climate is at equilibrium except when forced, the economy is at equilibrium except when hit by a shock. It suffices to study the two systems one at a time, and so-called integrated assessment models, which do exist, or YAMS, only couple very weakly, and they are sort of really Rube Goldbergish machines in which clearly a lot of thought went into putting in all the ingredients, but then, the parameters, as I said already, vary by factors of 2, 3, 10, 20. So an alternative point of view is that climate has natural variability on many time scales, years to millennia. The economy has so-called endogenous business cycles. So endogenous is just a Greek word that economists use for internal variability, internally caused. The coupling of intrinsic variability in the two systems might lead to surprises. And that's really what this is about. Okay, the need for endogenous models. This is out of a book by George Soros, published right after the terrible, financial shock that hit the United States and the rest of the world. The currently prevailing paradigm, namely that financial markets tend toward equilibrium, is both false and misleading. Our current troubles can be largely attributed to the fact that the international financial system has been developed on the basis of that paradigm. Okay? So, for those of who probably are numerous here who don't know what macroeconomics is, economics, aside from being the dismal science, has 3 subdisciplines. Macroeconomics that deals with national or regional economies as a whole, microeconomics that deals with individual households and firms, and econometrics, which essentially prepares a methodology for both of these. So some macroeconomic variables or indicators, GDP, gross domestic product, production, demand, capital, price levels, wages, unemployment, etc. So some of these are in physical units, others are monetary. Some are observable as time series, some are not. So for instance, when I started on this, I was pretty surprised to know that there's no history of capital through the 20th century. Nobody has a graph. Okay. Nobody has a graph of how capital evolved for the 20th century. You have data on GDP for about half a century, as I will show you, but not of capital. Okay, so, it turns out that the most reliable data are for the United States. So, things go up, okay? But on going up, there are little things which look really just like blips on this history, but in fact, they correspond to large oscillations in employment. So instead, if you do employment, you do unemployment. This is over 10%, which hurts a lot, okay? So what you need to do is to separate the long-term growth or trend from the short-term fluctuations, residuals after trend removing, which indeed grow in amplitude as the mean moves up, okay? So you need to also normalize. Again, here a tale of 2 theories, the real cycle and the endogenous cycle theories. In the real cycle theory, business cycles and economic fluctuations arise only from exogenous shocks, either real, i.e. not monetary, like changes in productivity or in energy prices, or from fiscal shocks. Aside from these shocks, the economic system is stable, or markets are at equilibrium, and there is no involuntary unemployment. Only lazy people don't work, okay? So deviations from equilibrium are damped more or less rapidly, so essentially this is AR1. Acting on the economy, therefore, e.g. recovery policies, is not useful. Just let it go. So you can tell that this is the popular theory these days for obvious reasons. The other hand, in endogenous business cycle models, cyclical behavior originates from endogenous instabilities in the economic system. Several instabilities have been proposed. Profitability investment, so you make a profit, you invest more. Delays in investment, income distribution, acting on the economy can therefore have positive effects by stabilizing it or shifting its mean state, i.e. Keynes. Okay? So here's a very simple non-equilibrium dynamic model, the one that I wanted to tell you the tale of fluctuation dissipation about, and then verify it with data. I'm just saying this because I'm going to need more than those few minutes. Okay? It represents an economy with one producer, one consumer, one goods that is used to both consume and invest. Based on the Solow model on which he got his Nobel Prize because he had that increase in the Western world while the communist world was stagnating or moving backwards. But in the Solow model, again, there were all sorts of equality constraints related to equilibrium. And for instance, demand was equal to production, which is not terribly realistic. So these were replaced by certain dynamic relationships that involve adjustment delays. So the equilibrium of this model is neoclassical in the sense that when it is in equilibrium, it will be the same one as the Solow model. Okay? Because of market adjustment delays, this model exhibits Keynesian features with transient trajectory segments in response to shocks, and it possesses endogenous business cycles. Okay. So here is a limit cycle of the model. Okay, it does have a sawtooth shape, so the expansions are slow compared to the recessions, which is realistic and which real cycle models don't have, because essentially AR1 it's symmetric with respect to going up and down. Okay, and the periodicity is roughly 5 to 6 years. Okay, this is a Hopf bifurcation diagram with respect to 1, so the model has 7 or 8 dynamic variables and some additional so-called diagnostic variables, for which you only have algebraic relations that link them to the dynamic ones. This is the control parameter or bifurcation parameter, the investment coefficient, how much you reinvest, as I said. And so here is an equilibrium, like in Solow model, and here is the range of the limit cycle once it arises. Here is an illustration of the limit cycle in GDP, and here it's projected, so from the 7 or 8 variables to the plane of employment rate and wages. So you see here it's elliptic. As you increase this parameter, you have transition to chaos. Okay, and you can see already kinks developing. And here you see that indeed the recessions become faster and faster, and the motion becomes more and more, the behavior becomes more and more irregular. Okay, so business cycles originate from the profit-investment relationship. I'm going to have to skip my usual jokes about Fukuyama, who had proclaimed the end of history. So again, higher profits, more investment, larger demand, higher profits. They are limited in amplitude by 3 processes: increase in labor costs when employment is high, constraints in production, and financial constraints. So one of the ideas is to give a more objective definition of the business cycle. The 2 acronyms here are the Bureau of Economic Analysis, which is a US government agency, and the much better known NBR, the National Bureau for Economic Research, which is a not-for-profit. Okay? Now, here comes the vulnerability paradox. When does a disaster cause greater long-term damage to an economy? During its expansion phase or during a recession? If I had the time, I would ask, as I usually do, for you to tell me what you think. But since I've already called it a paradox, you're going to know that it's not the obvious answer, or the one that economists used to think is obvious, that it's worse during a recession because you're in a recession. In fact, it's during an expansion. Again, we're not talking about the immediate damage, buildings collapsed, bridges destroyed, etc. We're talking about secondary effects. In other words, you've had all that destruction. What does it cost to bring your economy up to speed again? Okay. So here it is. Now what we're looking at is here is the production, and here are the production losses over one of those cycles. Okay, so it's a secondary thing. So here is a recession, and the losses are at a minimum. Okay, and here is an expansion, and the losses are at a maximum. So after you've seen this, you think about it, and you say, aha, it's obvious during a recession, It's going to be easier if a hurricane blew off your roof to get a roofer to put it back because he's out of work. So, you know, you're going to get it for less money. So, but this is only after the fact. Okay, then you're going to tell me, well, yes, but I can't choose when a hurricane hits Florida. Okay, so is there a net effect integrated over several business cycles? And the answer is yes. These are, you know, mean GDP losses in percent of baseline GDP, depending on this bifurcation parameter. So you see that there's a minimum here at a low value with with higher values of, higher losses at either 0 or higher values of investment flexibility. So, you know, maybe there's something to do. Maybe it tells us about how we should conduct our economic policy if we were to take into account these environmental threats. So, fine. So you get this result, and then you say, aha. So there is a dependence on the state of the economy of the impact of a natural hazard, but then you have at some point heard about fluctuation dissipation and that it might apply also out of equilibrium, aside from all the technical niceties that we've heard about. So maybe we are going to look at some actual data and find that there's more or less variability depending on the state of the economy. So again, I have to go much faster than usual. So, you know, you take these 50-some years of data from the BA. Okay, you have 9 variables, and here they are. And the vertical bars, these shadings, are the US recessions as declared by the NBR, based in part on objective criteria, but largely on subjective ones. Okay, so one of the purposes was to have a totally objective criterion of what a recession is, and it's not just a minimum in GDP. So again, applying these one of these advanced spectral methods, you question? No? Okay. You get indeed a peak at 5 to 6 years. You get also another one at 3 years, but which is maybe slightly less significant. In any case, I don't have the time to discuss it. This is just to show you, these are actual US recessions, so this is the longest economic instrumental time series, okay, like the Nile River. And this is from NBR via this sketch from Time magazine, and if you do this very fast, you're going to see you have 72 years and 12 cycles, so roughly 6 years, more generally 5 to 6 years. But again, with irregular spacings, and one of the ideas was to get what a typical business cycle, and thus describe what economists call the stylized facts, the lag, say, between employment and GDP and things like that. And so the net result that I wanted to show you is that if you define what we call here the local variance fraction, defined in a certain way in this within this SSA context, the signal fraction, okay, so the leading principal components of the SSA analysis are largest during the recessions, especially during the latter part of the record. There's some, you know, something here that might have to do with lack of quality of data or with other things. But, and the noise fraction, in other words, the rest, is minimum during the recessions. So, you know, it wasn't a bad idea to look at it in this way. Conclusions and outlook. So this highly idealized model exhibits fairly realistic endogenous business cycle period 5 to 6 years, seesaw shape, which the real ones don't have, fairly good phasing of indices, in other words, stylized facts. It displays its vulnerability paradox. This paradox is supported, for instance, by a report of the World Bank on the economic consequences of the Turkish earthquake called either Izmit or Marmara earthquake in 1999. So Turkey was in a slump. It actually stimulated the recovery. Reconstruction progress after 2 hurricane seasons in Florida. One of these was Hurricane Andrew, I don't remember which. And it confirmed my little story about the roofers. You know, the losses were smaller when the economy was worse off. U.S. economic data tentatively support a nonlinear fluctuation dissipation result a la Ghil. EBC, model calibration, I won't go into that. And again, we have similar work on European data, which was one of the colors on the cover with collaborators in Italy. And we did also some microeconomics in which we applied Boolean models to study the economy as a network of businesses, suppliers and clients, etc., and found that indeed the fact, which is usually not taken into consideration, that there are different delays in supplying a particular client does have an effect on whether the economy collapses or not. Likewise, whether you do get outside help or not, so you have percolation or don't, etc. So, the deeper motivations of economic modeling out of the New Yorker, obviously, for those who read it. Really, Carl, can't I mention the high price of kohlrabi without getting a manifesto? Okay, and here are some, okay, so here are some questions what I wanted to mention. So, are extreme events similar in nature to all other events, only larger, as per the great Gatsby, who says the rich are like you and me, only richer? Obviously, if that is true, then you can learn about the rich by having a much larger sample. But if that is not so, you can't. I'm sorry, I would have liked to have the slide of Vollmer on which he showed that, there are cases in which that is clearly not so. The large droplets are not like the small droplets. On the Gutenberg-Richter, straight line for earthquakes, it is not clear because there are so few very large earthquakes, 8.5 magnitude or larger, that you can't really tell whether they lie on that straight line or not. So those standard statistical theories of extreme value distribution do justice to all types of phenomena. Are there differences? So deterministic versus stochastic processes. We've had a whole session, that says yes, under certain circumstances, chaotic dynamical systems do obey generalized extreme value distributions, etc. Can long-tail distributions of events and periodic features coexist in a time series? Yes, and you better pay attention. Can we gain confidence in predicting extreme events from models of the underlying mechanisms? Well, I believe we can. So if there was any time for a panel discussion, I think it would be fun to discuss these things. And I'm just leaving you with a few references. Thank you for the extra few minutes. Okay.
Thank you very much. Time maybe for one comment or one question.
I heard from specialists that each economic crisis, when you look at the details, is in the details very different from all other ones. That one solves the problem for one crisis, and then the next one occurs for different reasons. Can you comment on that?
Yes, I can comment on that because people say exactly the same thing about every El Nino.
Huh?
Every El Nino.
Ah.
Okay? So there are two kinds of people. Those who say those things and look at the details, and the others who try to learn. I really don't think that you can learn, by fixating on a particular catastrophe. Okay? I mean, you have to learn, those who don't learn from the past are bound to repeat it. Okay? So that's my answer to that question.
I have a quick question regarding modeling. So in general, of course, say we have all this, models of increasing complexity, Earth system models, where still we have largely social models that describe impacts on society of changes in climate and so on and so forth. Do you think there is a perspective for the development of world models, in the sense where you have really an economy that is really coupled, so where you don't prescribe the CO2 path, where you can have a maybe correct but self-consistent path of economic development? Do you think is there somehow it's a reasonable thought or not? Because
it is reasonable, but humanity is not reasonable.
Yeah, of course.
Okay, I mean.
No, of course, yes. So there are
obviously our purpose. I mean, the more phenomena you put in, the more semi-empirical parameters you have to put in. And you know that I have this other talk about robustness and so on, which I chose not to give at this meeting. So I believe in a hierarchy of models in which you learn simple stuff from simple models, and then you have to confront it with data by having more complicated ones. But again, even in a general circulation model that is simply a model of atmosphere and ocean coupled, you know, how many parameters, I mean, not you because you've heard me, you know, ask this question. Anybody who doesn't really know, do you have any idea how many parameters there are in a GCM? 2, 3, 10, 20,000, you know, order of magnitude.
Let's say
You have a competition. Well, I'll tell you, more than 100. And actually, people used to just do tuning, you know, by trial and error, and now they are starting to realize that there's a real fundamental problem, and they're trying to do it more systematically. So 2 or 3 groups who did this more or less independently decided there was more than 100. 30 some are really, really important. Okay? So can you imagine that you get up in the morning and you want to get your favorite music station, you know, classical or rock or whatever, and instead of just having to turn the dial in 1 parameter, you have to turn the dial in 32 parameters? Well, you know, night will come before you manage to find your station if you do.
Okay, so okay, maybe we stop it. We have a time later. So thanks again, Michael.